Well, I'm here by myself, hopefully recording for you guys. Hopefully someone will join soon. In our old classroom, that way if I have any problems to do, I will do them on the board behind me, or I can do screen sharing if it's hard for you to see. But basically, we are going to talk about the gas phase, Module 11. We talked a lot about the liquid phase and the solid phase in the last module, mainly about the liquid phase and mixing solutions. I know it's been a long time ago, but you probably remember. So we are going to get more into the gas phase this module. So one thing you do need to know is that for solids and liquids, scientists measure their mass and volume, as you've seen before. But with gases, they also measure their pressure. So we need to talk about what pressure is. Pressure is the force per unit area exerted on an object. And if you're following along with me, I'm on page 383 in your textbook. So you can write that mathematically. I'll write it here behind me. I don't know if you can see that. Pressure equals, oh, it's backwards, force per area, per unit area. I'll have to figure that out because it's definitely backwards. Oh, I can do the screen mirroring. Sorry, this is new to me. We will get better at this. I will get better at this. Let's see if I can figure out how to do that. Okay, maybe that worked. Let's try that. Okay, so pressure, the force exerted on an object per unit area. You do not have to memorize that equation that I just showed you. It's not necessary. The main reason we talk about it is so that we can talk about the unit we will be using for pressure. And the unit is going to be, okay, so the unit for force that we've used before is newtons, and the unit that we've used for area is meters squared. So newtons per meter squared, there's another name for that. It's called the Pascal, P-A-S-C-A-L, and that is to honor a French mathematician, scientist, and philosopher. He revolutionized the study of probability as well as the sciences of chemistry and physics. And he was also a philosopher who provided several convincing arguments for the validity of the Christian faith, which I thought was really cool. So it's named after him. The unit for pressure is Pascal. Let's see. I'm going to write it and see if you can see it the right way now. You see that? Yeah. So that's our unit for pressure, Pascal. That's what we'll be using from this point forward. And the important thing that you need to realize is that gas exerts a pressure on any object that it comes into contact with. Because as we've talked about with the speed at which molecules move, in the solid phase, they're moving very, slowly. Liquid phase, a little bit faster. Gas phase, they're moving a lot, and they collide with each other a lot. So that means that because they're moving around very quickly, they collide with things that get in their way, which is what then causes the pressure upon the object. And since our atmosphere is composed of a mixture of gases, the atmosphere must exert pressure on any object with which it comes into contact. So I'm sure you've heard of atmospheric pressure, and the weather can affect that sometimes too. Every person, animal, object on Earth is under atmospheric pressure. Hey Garrett, it's just me and you. I've already started, so if you want to go back, you can see the beginning.
How do I do that?
I'm not sure. I'm learning too, but it says it's recording. So I'll see if I can figure that out at the end, how to go back, and I'll let you know. But I'm on page 383 in the textbook, and so far I've just talked about pressure and how gases exert pressure on any object. So that's what I'm talking about. And the unit that we will use, I had to flip my screen, is Pascal for pressure. And it's named after a scientist. So that is going to be our unit. Okay, so because the atmosphere exerts pressure, we use that as a measurement for pressure. So Pascal is not the only unit. We also use atmospheres. So on page 383, you'll see towards the bottom where it talks about 1 atmosphere equals 101.3 kilopascals. So we say that a gas exerts 1.000. You probably can't see that. Can you see that? Let me write it. Is that better? 1.00 atmospheres if it exerts 101.3 kilopascals. So these numbers are equal. And you'll use both of those units for pressure. I'm sorry, this is terrible. I'm going to figure out how to do this better moving forward. Okay, so you'll use those units. You'll use millimeters of mercury and torrs. So turn your page and go to 384. And at the top there, you see the table 11.1. You need to memorize that. That's 4 different units for pressure that we will use. And in a lot of your equations, you're going to be converting between those. So you'll be converting atmospheres to torrs or torrs to kilopascals, all that kind of thing. So you do need to know that table right there. I'll put a star, circle it, whatever. So that's what you need to know about pressure. And there are instruments they briefly mentioned that can measure pressure. We won't use that too much right now, but I'm sure you've heard of like barometers and that type of thing that measures pressure. All right, moving on. Boyle's law at the bottom. So this scientist named Robert Boyle did lots of experiments, like hundreds, to determine how the pressure of a gas relates to its volume. And he determined that as long as the temperature stayed the same, the product of a gas's volume and its pressure is always the same. So you see the equation at the bottom, PV equals constant. You don't need to memorize that. Okay, Haley says she's not coming. You don't need to memorize that equation, but it's just, we're gonna combine a couple equations together later on, just kind of wanna understand what it means right now. So what that means is that if the product of the pressure and the volume stays the same, that if the volume increases, the pressure will decrease. And opposite. So if the volume decreases, the pressure will increase. And you see that in figure 11.2 on page 385. So it shows you there, the little blue thing on top is the mass that they've set on top of this that's causing pressure on that gas within the gray area. And so the mass isn't putting a whole lot of pressure in the first picture there, which is why the volume is so large. But if you put more pressure on the gas, you can see the volume decreases. So more pressure, less volume, like in the third picture there, or not much pressure, high volume, as in the first picture. So they're related, opposite. That's the main thing that you need to know about Boyle's law. And it makes sense because if we increase the volume that a gas occupies, then there's more space for them to move about. They're not going to run into each other, the molecules, as much because there's a huge space. So if you have a smaller space, they're going to be bumping into each other a lot, which is going to cause a high pressure. So it kind of makes sense if you understand the kinetic theory. However, Boyle did not have that. So like I said, he did hundreds of experiments to figure that out, which is pretty impressive. Also, we could say, if you turn the page, 386, that the product of a gas's volume and its pressure under one set of conditions must be equal to the product of its volume and pressure under any other set of conditions. So that's that P1V1 equals P2V2. Again, don't memorize that. We're gonna memorize another equation later on that involves this. But that just tells you P1 and V1 are the pressure and volume of a gas under one set of conditions, and P2 and V2 are the pressure and volume of the same gas under another set of conditions. So maybe a different temperature, something like that. So don't memorize that, but just understand how they're related. So pressure and volume oppositely related. Higher pressure, lower volume, lower pressure, higher volume. Okay, so the next law that we'll learn that we are going to combine with that law is Charles' law. And this was a French scientist, and he found that the gas's temperature affected the pressure as well. So if the temperature was raised, the volume that the gas occupied increased as well. So you can see that in figure 11.4 on 387 there. So if the temperature is higher, then the gas occupies a higher volume. And if the temperature is lower, it occupies a smaller volume. I'm turning the page and you'll see a chart, figure 11.5. Sorry, Haley was texting me. Okay, so you'll see there, when the temperature is warmer, they occupy higher volumes always. So if the temperature of a gas is doubled, its volume doubles. If it's halved, if the temperature is lowered halfway, the volume will decrease by a factor of 2 as well. So Charles's law, you do need to know, says at a constant pressure, the temperature and volume of a gas are linearly proportional. So that equation there is going to be V divided by T. So whereas pressure and volume were oppositely related, volume and temperature are going to be going at the same rate. As you can see there in the chart, if the volume increases, temperature increases, vice versa. So let's see what we want to talk about. And it makes sense because if the temperature increases, then the molecules have more energy, so they're going to be moving faster, which means they're going to have higher space because they're going to be moving around a lot more quickly, a lot faster, a lot more. So let's see. Sorry, I was going to see what I want to talk about. Since volume divided by temperature always has to stay the same, then the volume divided by the temperature under one set of conditions will be the same under another set of conditions. So that equation there on 389, V1 divided by T1 equals V2 divided by T2. Whereas volume 1, temperature 1 is the same gas as in volume 2 and temperature 2, just a different set of conditions. You don't need to memorize that. We will combine them later on. I do want to go back to that figure 11.5 that you see on 388. And notice that each gas there has a different line. So like the green line is helium, the pink line is CH4, and the blue line is hydrogen gas. So no matter what gas you put on the graph, the line that goes through the gas's data points will always hit negative 273.15 degrees Celsius when the volume is 0. We can never cool something lower than negative 273.15 degrees Celsius because you can never have a volume of zero. Then the gas wouldn't exist because all matter has to take up space. So something interesting about that temperature, for centuries, scientists have tried to cool things down to a temperature lower than that, but they can't. So the lowest temperature it says that has ever been reached was 0.00000005. They can't get to 0 degrees Kelvin. They've never been able to do it. So that temperature, that 273.15, should look familiar because you had to convert to Kelvin in a previous module. And that's why it's that temperature. So you always add 273.15 to convert to Kelvin, from Celsius to Kelvin. So we'll be doing that a lot in this module, converting to Kelvin for our temperatures. So go ahead and turn the page and we'll just talk briefly about that graph a little bit more. You'll see, well, you can stay on that page. I'm just going to talk about it. So the graph on 11.5 there on page 388, The dashes means that that's temperatures that they've never recorded before, but they're doing something called extrapolation, which means they're following the trend of the graph. They're kind of just predicting that's what would happen, even though they don't have any evidence for that. What's interesting about this is it's not a whole lot of missing information there that they're filling in to follow the trend. In general, extrapolation is okay as long as it's a small amount of data that you're like filling in that you don't have evidence for. But what they wanted to point out, which I thought was very interesting, was that for evolution, Charles Darwin extrapolated a huge amount of data. So he said that when he observed the finches on the Galapagos Islands, that their beaks were changing, their feather colors were changing, and their body sizes were changing based on their environment. They were adapting. And those were very small changes compared to going to a whole nother species. So he took the changes that he saw and he extrapolated a great amount of data. And that's how the theory of evolution started. So that a careful scientist will only make small extrapolations. So I thought that was kind of interesting. You can read more about it on page 390 if you're interested, but I thought it was cool. So really that's all we had for today. We have a short class. We're going to talk about pressure, going to talk about Boyle's law, Charles' law. Tomorrow we're going to combine those two laws together and we'll have an equation that we'll use, and we'll do a lot of examples of that together. So hopefully our other classmates will join us for that. But yeah, that's all I had for today. Any questions on anything that we talked about?
Not really.
Okay. Well, just send me your homework by 12. I need the 2 homework assignments, the 5 notes, and the study guide, the review questions, the practice problems. And
For last week?
From last week.
Okay.
By 12 o'clock, and I will grade it and put it in Homeschool Minder for you. And yeah, so
I'll just send you pictures of it.
Yeah. So if you're watching this video later, we are just reading from page, let's see, 382 to 391 today and stopping right there before the combined gas law. If you want to go back and read it, get more information, because like I said before, I can only briefly talk about it since we don't have a whole lot of time. But that's all I had for today. So thanks for testing this out with me. We will, I'm sure, kind of tweak some things as time goes on and make this better for everybody. And if we want to do a different time, because clearly nobody likes this time, we can talk about that and just see what works for everybody. So let me know, give me feedback, and let me know if you have questions.
All right.
All right.
Thank you.
Thanks for coming.